hapa Discord.
Live streaming is on. Okay, sawa, niko unmuted on Jitsi, alafu nikiingia Discord nifungue share screen.
Yes, nimeona stream imeanza.
Okay.
So bado hujashare sasa present kwa Jitsi pia.
Pia kwa Jitsi.
Yes.
Okay. Wewe.
Yes.
Hapa kwa Jitsi naona inashare.
Sasa enda kwa screen yako sasa. Enda tu kwa screen. Enda kwa tab yako.
Iko sawa sasa. Sasa sijui mnaona nini?
Tunaona mimi naona hiyo page ya Jitsi.
Okay. Sani nimeconfuse. But si inaonekana pia on Discord, yani.
Inaonekana pia kwa YouTube inaonekana 01 binary search.
YouTube.
Yes.
Okay.
Tuna stream kwa Jitsi. Yeah.
Okay, so I start.
Hapa ndio mimi sioni. I don't know kama Kibandi unaona anything hapa Discord. I think you can start slide.
All right. I'm hoping everyone can see. Okay. So in case
before start ukuna scroll pole.
Sawa.
Huwa inaflika.
Okay. So just scroll pole. Alafu pia if by any chance ni drop off at some point nita hata kama mtu anaweza nishtua on WhatsApp maybe because naogopa internet itahang, but ni sawa. It's okay sahi.
Sawa, haina shida.
Okay. So hi people. I'll be presenting on binary search. This is an algorithm since we're in the series data structures and algorithms. So I'll be presenting on the binary search algorithm. Yeah, I'm trying to see a minute, Kwanzaa, I confirm something. It's a searching algorithm that works differently. I don't know if you have seen the linear search, but linear search is the normal search. For example, if you have a book and you flip page by page evo until you find whatever you're looking for, that's an example of linear search.
Normal search, for example, if you have a book and you flip page by page evo until you find whatever you're looking for, that's an example.
Rodney, I can hear myself.
Linear search.
Rodney, there's an echo. I can hear myself from your side, I think. Rodney, please mute. Okay, so great. Higher. So I'm saying binary search is an example of a searching algorithm that doesn't necessarily follow the normal procedure. If you're searching for something, the normal procedure that your mind will automatically go to is just go one item after another. If it's a book, you'll just flip the pages one by one until you get it. But binary search is different. It works on divide and conquer. So basically, if you have a given data set, it will work by splitting the data set into sub arrays ama subsets, and then splitting those ones further until it gets to the item you're looking for. Like for example, it identifies the middle item. If you have a list of 20 items, it will identify the middle item, and then whatever you're looking for, it searches whether it's before the middle item or after, and then it goes with that half. Now in that half again, it splits it into two, searches whether it's before or after, goes with that the half where it's in. Yeah, then it's that repetitive until it gets to the actual item you're looking for. It will make a lot more sense when you look at it in the example of in a given example that we're going to see in a few. A condition for this, however, is that the list you have, it should be sorted. Like it should be arranged in ascending order. For example, it should already be sorted. It can't be just random values. If you have numbers, they can't just be random numbers in whatever size. It should be sorted from the smallest to the largest, and then now from there you now begin your search. If it's not sorted, first use a sorting algorithm, sort it, and then now you can do the searching. The time complexity is logarithmic time, that is O log n, that is the time complexity of this particular search. For example, linear search is usually O(n), so this one is O log n. The list is divided in half every time, so let's just get to how it works so that you can be able to get an overview of how it works. For the functionality, I hope I am scrolling slowly. Okay, that's okay. So we will start with a given list. We'll work with an example in this case. We begin with a sorted list, and then we're going to create our sub-arrays until we find the item we're looking for. We're going to be using the mid values for creating this sub-arrays. So assumption in this example that we have is our array is sorted. As you can see, our array is sorted. It consists of 10 elements. 10, 14, 19, 26, 27, 31, 33, 35, 42, 44. So those are the 10 elements we have, and they are arranged from the smallest to the largest. We are looking for the location of 31. As you can see, 31 is slightly blue. So that's our target. That's the target element that we are looking for. We want to get the position of 31. So the question maybe was something like, we have a sorted list of these values. How do we get the value of 31 using binary search? Yeah, something like that. So that's what we're using. So we want to find the position of 31, and we'll use binary search for this. The first thing we do is to identify our mid index. Now in this case, our indexes range from 0 to 9, the first index or the lowest being 0, and the highest index or the last one being 9. We want to find the mid index. Now to find the mid index, we'll take the lowest index, in this case 0, plus the highest minus the lowest index divided by 2. So 9, the highest minus the lowest, yes, divided by 2. So 9 minus 0 divided by 2. And then the answer will be rounded down. We don't take the highest minus the lowest directly because we're using int. The index value is usually an integer int, and if we use the highest minus the lowest directly, it would surpass the limit here, the data type, of the int data type. So this formula is the one we use. For example, in this first one, we'll take 0. You can use the cursor. So here's 0 plus 9 minus 0 over 2. So 9 minus 0 over 2, which is 9 over 2. 9 divided by 2 is 4.5. Plus 0 is still 4.5. But we round it down. If you get an answer with a decimal, you round it down. When you round it down, the mid index is 4. Okay, so our mid index in this case is 4, which is illustrated in this photo. It's pointing at position 4. Now at the mid index 4, what we do is we look at the value of the element at that position. This value in our case is 27. Remember, we have our target value as 31. And we have found our midpoint
amerudi. Okay.
Hey, sorry, my internet is it's all over the place. Hey, I'm sharing. Kila mtu anaona? Mnaona? You can see my screen.
Hey, yeah, Jitsi. Yes.
Okay, Discord.
Hey, tuko Discord, yes.
Oh, okay. Sawa, nilitoka wapi?
Ulikuwa naendelea YouTube, ulitoka Discord.
Oh, so Discord nilitoka wapi?
Me the last thing nilisikia ni complex. Order N.
Okay, so I'll just start the example again. I think that will be better. Yes, the after order. Yes, so we start with the functionality of binary search. Now we're going to have an example of a list of 10 elements, an array of 10 elements. In this case, our elements are 10, 14, 19, 26, 27, 31, 33, 35, 42, 44. Our elements range from between 0 and 50, and then they are arranged from the smallest to the largest. So you can see our list is already sorted. So now we're doing the binary search. In this case, another assumption we have is that we are looking for 31. So our target is 31. We want to use binary search to find the location of 31 in this list. At what index is 31? That's the question. So our list is sorted. We have the values there. The first thing we need to do, let me move slowly. Yes. The first thing we need to do is find the mid value. The mid value using the indices, where 0 is our least or lowest or smallest index, and then 9 is the largest, or yes, the last index. So from 0 to 9, we need to find the index of the mid value. To get our mid index, we'll use the formula lowest index plus highest index minus lowest index over 2. What we will have done, maybe it would have taken the highest minus the lowest over 2, but we won't do that because an index is an integer. That's the data type. So if you use highest minus lowest over 2, you could highest minus lowest, you could get a value that surpasses that data type. So we'll use lowest plus highest minus lowest over 2. In this case, our lowest index is 0 and our highest index is 9. So if we replace it, we'll get 0 plus, let me use the cursor, 0 plus 9 minus 0 over 2. Literally just this formula, replace it. So lowest index is 0, highest index is 9. So if we take lowest index 0 plus highest index 9 minus lowest index 0, divide by 2, we'll get 9 minus 0 is 9 over 2. 9 divided by 2 is 4.5. Plus 0 gives us 4.5. Now, if you get a value, a decimal, round down your answer. The answer should be rounded down. So 4.5 rounded down, in this case, we get 4. Therefore, our mid-index is 4. So that's what we'll work for as the first mid-index, 4. If we have 4, we now start with that. We have our full list from index 0 to index 9. with our mid value being at index 4. So we take the value at index 4, 27. And remember our target is 31. This one that is slightly blue, yes, 31. Our target is 31. So we now compare 27 and 31. Is 31 less than or greater than 27? If it's greater than, we'll continue with this upper half, this upper subset of the array. If it's less than, we'll continue with this lower subset of the array from 0. If it's greater, we'll continue with this upper subset till 9. 31 is greater than 27. Therefore, we use the upper half. So we'll use this upper subset to search for the index of our target value, 31. As you can see in this next photo, the lower half has been discarded. We're not using this one. We now focus on the upper half. Now what happens is, if you're moving, the lowest index changes. If you're moving from, your lowest index is changing from 0. But what will be our new lowest index? Remember, we need to get the lowest index and the highest index in order to find our mid index. In the first case, our lowest index was 0 and our highest index was 9 because it was the entire list. But now we've split the array into 2. So our highest index is still 9, but our lowest index will no longer be 0. It will change. So if we change and move to the upper half, we get a new mid index by adding the mid index we used, which was 4, which gave us 27 as our mid value. That mid index plus 1. So our mid index 4 plus 1 gives us 5. 5 becomes our new lower index. So when we're using this upper half subarray, our lower index is 5 and our upper index is 9. That's the limit of this subarray that we're using. We now proceed from there in the same way. We use the same iteration. We split our array into 2 again, confirm whether the value is in the upper side or the lower side, and then split it further until we get an answer. We're okay until there. Okay, I hope we're still okay. If you're lost somewhere,
Yes.
So thanks. But if you're lost somewhere, feel free, Pierre, to just say where you were left off. Then I can get back to you. So now with our new lower index 5 and upper index 9, let's find our new mid index. Using the formula we had, our mid index should be lower index plus higher index minus lower index over 2. So in this case, our lowest index is 5 plus highest index 9 minus lowest index 5 over 2. 9 minus 5 is 4. 4 over 2 gives us a 2. 5 plus 2 is 7. So our new mid index will be 7. Let me move it. Yes. Just like in this photo where the arrow is pointing, our new mid index is 7. We'll use that mid index to compare the value at that mid index with the target value that we want to find out whether it's in the upper half or the lower half. It's the same thing. Great. So at 7, the value of the element at position 7 is 35. Our target is 31. 35 and 31. Is 31 less than or greater than 35? 31 is less than 35. Therefore, we'll use the lower half. We'll use this lower half that goes up to index 5. Okay, let me scroll there. The mid index is higher, therefore we use the lower half of the list to search for our target value. When we are now using the lower half of a list to search for the target value, let me move it slightly so that you can compare higher. In the subarray we had just before, our lowest index was 5 and our highest index was 9. But now we have split this subarray into two, and we are looking at the lower half. Our lowest index therefore remains 5, but our highest index will change. When we were changing from the full subset of 10 elements to a smaller subset, we used the upper half. When we're using the upper half, the lowest index was changing. We took it as mid index plus 1. But now this is different because we're using the lower half. So we are retaining our lowest index, but our highest index is changing. It's no longer 9. We're now moving from 9. So if our highest index is changing, the new highest index becomes the mid index, the one we got 7 minus 1. So our highest index will now be 6. That's a key difference. When you're using the upper half, the highest index remains the same and the lower index becomes the mid plus 1. But when you're using the lower half, the lowest index remains the same, but the highest index becomes the mid minus 1. That's a key point. So in this case, it will be our mid index was 7. So 7 minus 1 gives us 6. This means our new half will have elements from index 5 to index 6. Hi, let me move it down. Yes. One minute. Nimekusikia, acha na reconnect. Hello. At what point did I drop off again? Hi, am I audible?
Yes, you are.
Okay, at what point did I drop off again? Sorry. Ama what was
hapo palipa kuchange mid index ikue 5.5.
Aya, sawa. Let me repeat from the mid index. Sorry, I apologize. My internet is not the best. But sawa, I'll just proceed. Let me move the mid index. Let me just repeat your concept here, mid index all together, because it's a key point. So we had our when we first divided our array, and we were left with the array from index 5 to index 9. We then got our mid value at index 7. At index 7, we got our new mid value. Then we compared. Our target value is 31. At index 7, the element has a value of 35. So is 31 less than or greater than 35? We found 31 to be less than 35. So it's in the lower half of this new subarray. Now, when in the lower half, what changes is, let me move it up kidogo there so that we can see. Initially, when we had our full array, it was from index 0 to index 9. We got our half at index 4, meaning our highest index 9 is retained, but we don't have our index 0 anymore. The lowest index is the one that will change because we're using the upper half of the array. That's why we had to change our lowest index by finding the mid index, which was 4 plus 1 to get 5. 5 was our new lowest index and 9 was our highest index. But in this case, we're now shifting and getting the lower the lower half. We're using the lower half because our target value is less than the value at the midpoint. Now, when shifting to the lower half, our lowest index, which was 5, will still be our lowest index here, which is 5. But since we are splitting it into 2, our highest index won't be 9 anymore. We'll need to shift our highest index. When shifting our highest index, we take our mid index that we got, which is 7, minus 1. You get 6. So our new highest index will be the mid index minus 1, which gives us 6. So I was saying that's a key point you need to know. If you're shifting to the upper half and your highest index is remaining the same, your new lowest index will be the mid index plus 1. But if you're shifting to the lower half and your lowest index remains the same, your new highest index will be the mid index minus 1. I hope that one is understood. It's a key important point in calculating your next midpoints. Once you have that dynamic of the highest index and the lowest index, you'll always be able to get your midpoints. And if you can get your midpoints, you'll always be able to divide your array into sub-arrays and find the value. So we can proceed. That was the point. We split it into 2, got our mid as 7. So our new highest is 7 minus 1, which gives us 6. So our new subarray has elements from index 5 to index 6. Those are the two. Higher. We now have our highest and our lowest. We can now calculate. We can calculate our mid index. Mid index is lowest index plus highest index minus lowest index divided by 2. In this case, we'll take lowest index as 5 plus highest index, which is 6, minus lowest index, which is 5, divided by 2. 6 minus 5 is 1, divided by 2 is 0.5. Okay, 0.5. So 5 plus 0.5 gives us 5.5. But we said anytime you get a decimal, you round it down, round your number down. So our mid index will be 5 in this case. Higher. There we go. Our mid index is 5. Now we get the value at our mid index. The value in this case is 31. Our target value with the value at the mid index, they are equal, which means that we found the answer. We found the location of our target value, and the location is index 5. That's our answer. So that's how binary search works. If you think about it, binary search is like if you're using a dictionary and you're looking for the word jungle. So instead of going from A, B, C, D, page by page until you get A, B, C, D until you get to J, then you start J, A, J, B until you get to J, U until you find jungle. So instead of searching all that way, what you do is say the alphabet has two halves, A to M, then N to Z. J is less than, so you start with the upper half, then you divide it into 2. If you divide it into 2, get your letters until you find where J falls. Then but that person who will decide to just move directly from the first page, from page 1 and go directly looking for J, that's an example of a linear search. You're just moving directly through the elements one after the other. Binary search helps you split them into 2. That's the basic functionality. That's how binary search works. And I hope that one is understood. That's kind of the base of it. Recursive binary search is such that when you're writing code, if you think about it, this code has a lot of checking, splitting. If this is equal to this, if this is less than this, if this is greater than this, do this. And then you check again. If there's a lot of iteration, there are a number of loops. So instead of doing that, you can have a recursive binary search such that it just automatically calls the binary search function again. You'll see it in the code. It will be same in the code, but it will just call the binary search function again. Yeah, instead of repeating yourself all the time, you can just call the function again. Then it does the same thing over and over. Advantages of binary search. I've explained binary search is like, dividing the dictionary into half, either moving that way as opposed to moving from the start to the finish. So one of the main advantages is that it's very useful for large data sets. If you have a very large data set and you can't just start, for example, if you think about worst case scenario, if the item you're looking for is zygote in the dictionary, if the item you're looking for is zygote in the dictionary and you start going page by page, that's linear search. You'll be there for a long time, especially if you're using this 10th edition, 11th edition, Oxford Dictionary. You'll be there forever because you'll have to go through the elements one by one. So if you have a large data set, you automatically divide it into two, get your half, move with it. It becomes easier when you're searching through a very large data set. Another example is it also narrows down the search by eliminating half the list after comparison. Immediately after comparison, it eliminates half the list. You can imagine if we could, this is just my imagination though, but if we could find people, if there's a missing person, if we could find someone by binary search, it would make it so easy. Instead of going through the whole of Nairobi, we just take Nairobi, use the where are they're here, we eliminate this half, we use this half, instead of having some people going to Westlands, some people going to Ngong Road, some people going to Mombasa Road, some people going to Thika Roads, and we'll be able to divide it into half. So it narrows down the search. Naturally, it gives you a narrower area to focus on. And then it enables you to know whether the item being searched is before or after the mid position. So that, again, is tied with the other advantages. When you know whether it's before or after, you can be able to narrow down easily. Disadvantage, disadvantage is that it only works on sorted lists. That's why I was saying the assumption is that we're working with a list that is sorted, and if it's not sorted, you have to use a sorting algorithm first to sort it. As in, there's no two way about it. It has to work with a sorted list. And then it's an overkill for small data sets. If you have a very small data set, if you have a data set of for it, a very, very small data set, it doesn't make sense to have it search half, yet all the time you could have just moved, maybe there were just 3 items, just move 1, 2, 3 and check if they're those. But now this one, you'll have to get a mid, compare if they're the same, get the upper half, change the highest index or the lowest index, get a mid again. Yeah, if it's a very small data set, it's not worth it using binary search. That's why an advantage is that it's better for larger data sets. And also it's more complicated than linear search. Like I said with the dictionary example, it's much easier to just flip page by page, but in order to use binary search, you need to have some kidogo or some little bit of math knowledge so that you can be able to know how to divide in half, where to divide in half, and all that dynamic, as opposed to linear search where you just move from the first to the last one. Applications, it implements features like autocomplete. That's what I was able to find. Autocomplete, because autocomplete is a very large data set. So it's easier to use binary search in a large data set like that. You can use it to find prefixes because those are small parts of words, and again can be a very large data set. I think can also work on suffixes and the likes. Now this is the example in code. It's basically an explanation of what I have said, but I can just quickly run through it. I have the Python and Java examples. We'll just run through one. Then it makes sense. Let me find the right position. Okay, there we go. For example, if we're using this Python code, our initial start, the first index will give it as 0, and our end will be the maximum value of the array minus 1. I hope we understand where that comes from, but let me just explain. if we have 10 elements in our data set, such as the one I used to explain, if you have 10 elements in a data set and your first element is at index 0, then it means your final one will be at index 9 because 0 is counted as your first element. So to get the final one, the function len of our array, we called it r. Oh, I should have said this, sorry. We are passing this to this function, we're passing r, which is our array, our list of elements, and target, which is the one we're looking for. Those are the two main things that we need to start our searching. Okay, so back here at n, you find you use the length of the array. Len of our array called r, len of r will give us the total number of elements in the list. So in this case, it will give us 10 minus 1, because since we started at 0, the final one will be one number less than the total length. So it will be 0 to 9 in short. That's what they're saying, if it's 10. So you check, and then you get that, you get your start and end. Then our first loop, while the start is less than or equal to the end. It will only loop while the start is less than or equal to the end. That is now within range. We first of all find our mid element, and we use that formula. We use our formula, we get the mid. Then you check if the index, if our array element at position mid is greater than target, then it means it's in the upper half. If it means it's in the upper half. It means our target is in the lower half. The target is lower, sorry. The mid element is greater than the target. So our target is in the lower half. If it's in the lower half, our start remains the same, but our end is changing. Our highest index is changing. And when we change the highest index, we take the mid minus 1. So this becomes our new end. Or else, if our mid, the value at the mid index is less than the target, means our target is in the upper half, it's larger than that mid value, then our end does not change, but our lowest index will change. Okay, let me just repeat that iteration in the code. I think that's where I've dropped off. We have our start and our end initialized at the start. So while the start is less than or equal to the end, so while the elements are within the range of our array, we get our mid position using the fixed formula, finding the mid. Okay, finding the mid. And then we now check if our array item at the mid index is larger than the target. It means our target is in the lower half because the mid item is larger than the target itself. So this target is in the lower half. Therefore, we need to focus on the lower half. And if we're focusing on the lower half, then our start remains the same, but our end will move. And our new end will be the mid index minus 1. The way it was explained earlier on. Else, if our value, our array value at the mid index is less than the target, meaning our target is larger than this mid value. So the target is in the upper half. If the target is in the upper half, our end will remain the same, but our start value will change. Our lowest index will change. It will now become the mid value plus 1. Okay, that's what I was explaining there. Else, if it's not larger than or less than, it means it's equal to. So we've actually found it. Hooray! So if we've found it, we now return the mid. We now return that position. Yeah, that's basically an overview of the code. It can also be done in Java form, the same thing. If we have a certain list and our target is this, in our binary search, we send the array and the target. And then it should print out the answer. So it does the same thing. It initializes our start and an end, which is the length minus 1. Then while the start is less than or equal to the end, yeah, still on, is less than or equal to the end, we get our mid, and then it checks if the target is less than the mid. Please mute, there's a lot of echo. Thank you. Yes, that's the basic idea. This is just another language, but it's the same syntax. If we go to a recursive binary search, the difference is that the recursive binary search will just call on, okay, my internet is still there. We'll just call on the function and it will do the same thing again. That's basically what I'm explaining. If we give this array and give it a target, then send it to the recursive binary search, it will do the same thing, but now it will keep on iterating. That's basically, yes, that's the overview. That's the overview of binary search. Yes, if you research, you'll find it's used in many, especially very large data sets. They use binary search, and it's a very essential tool. If you understand the working, you're good. You can use it to apply. You can use it to apply it in various situations and questions. There's also a lead challenge here. I can send the lead challenge and also the link to the lead. How do I call it? Where lead have their content, more content on binary search. You can go and go through their content and how they explain it and attempt the challenge. And that is it from me. Thank you.
Thank you, Sly. I think that's it. So I think Sly unaweza tuma the lead code challenges hapo kwa voice chat. We can all work on them. So if you'd like to listen to some music, join the social zone. The resources will be shared hapo kwa voice chat. Yes. So Sly anatuma the lead code challenges kwa voice chat. So if you want to listen to some music, ingia social zone. Thank you. You can meet. I think we can meet next time. Yes.
Sawa. Thank you for listening. Thank you for attending. I hope you have learned something. It has been an honor. Rodney, can I stop the YouTube stream?
You can stop it.
Okay. Are there any questions though before I can exit Jitsi.
Questions.
I can exit Jitsi. Rodney, can I end the Jitsi call?
Unaweza end. Yes. I think